for future of all Earth system modeling, or only Earth system modeling at the Met Office?
No, it's pretty much a meaningless title. And actually, it's what I've put together is a number of thoughts from this week, a number of thoughts from the TGNES meeting we had in Seville in March, and a number of results from the Hadley Center. And I will go very briefly through the plans that we have at the Hadley Center. Okay. Yeah, we thought quite a bit during this week as to why we needed Earth system models. And I think there are basically three main reasons. The first one is to include a number of forcings which involve the biosphere and the atmospheric chemistry. And I intentionally omitted the word radiative here. So I'm not just talking about radiative forcing, but forcing in general. And some forcings are non-radiative, like land use, aerosol indirect effect. There is quite some debate whether that is a radiative forcing or not, etc. So the first reason is to include forcings and feedbacks which involve the biosphere and the atmospheric chemistry, and which are of potential importance to the physical climate. Yeah, first reason. Second reason is to look at climate impacts in a more holistic way, because some of these impacts, they're dependent on climate change, of course. If the impact is just dependent on climate, then you can probably argue you can look at it offline, so you don't need to couple the model. But if the impact is really very much dependent on weather, then there is an argument that you want to look at it online in an Earth system model, because that would be probably, you would have to store far too much data to sort of look at it offline. And for instance, coastal surge really depends on surface pressure, on precipitation, and that's something, it's just easier to diagnose that online than storing terabytes of data and doing the analysis offline. If the impact feedbacks on climate, then that's another reason to look at the impact online in an Earth system model by opposition to offline. So we are gradually moving in a stage where the impact assessment will be moved towards the Earth system modeling. And just an example for this one would be crop. Climate change will affect crop, but crop in return will affect the climate because of evapotranspiration, flux, and etc. The third main reason to have Earth system models is to inform climate mitigation strategies, and we've discussed that quite a bit this week, so I'm not going to go through that just beyond what I put here. We want to avoid dangerous climate change, for instance the Amazon dieback, and that's best done in an Earth system model. And we want to verify the plausibility, and we want to bring consistency with the emission scenarios. And we've heard about air quality control policies, the competition between food production and biofuels, and that's a function of the economy, but it's also a function of the climate. And the cost of adaptation, which has to be included in these models, is also a function of climate change. So that's the three main reasons. So it's moving on my screen, but not on the main screen. Okay. So this is just a small sketch of Earth system models. You're very familiar with that, the physical climate system, and then some more components which are gradually taken into that framework. Aerosols and chemistry, dynamic vegetation, land and ocean carbon cycle. But the thing we haven't discussed so much today is that there will be some intersection between impact models and Earth system models. So there is a little bit of impacts which has to be done here. Then there's still a number of impacts you can do offline, and there is a number of impacts where you've got to go to higher resolution using regional models or even very high resolution models. And something which isn't clear to me, I've got different answers depending on who I talk to, is how much consistency you need between the Earth system model or the climate model and the regional model here, which is used for downscaling the climate change and diagnosing the impacts. And some people they want a lot of consistency, so they want a regional model which is as close as possible to the climate model. And some people, especially from the impact community, they say, well, it doesn't care so much because we're doing so bizarre things anyway. We're not very consistent, so
if you use a different GCM, you get a different
yeah,
result. Anyway,
that's
they
it.
do all the time. So
Yeah, so they say, well, no, it doesn't matter so much. You can have a
the
different
impact model itself has a hydrologic cycle which has different terms in it and balances than the GCM producing the precip that was going into that well.
Well, at Hadley, we're trying to have a regional model which has got the same parameterization as the climate
So, for
model.
example, let's say you were using output from the regional model in the
yeah.
series wheat model. That wheat model has
yeah.
its own hydrologic cycle, which is different,
Right.
with different approaches than.
Yeah, you would have one more model here, which is the impact model, right? That's something we can start thinking about, anyway. So I've lost the mouse now. Yeah. The model setup. For a number of applications, we will need a full Earth system model. But for some other applications, we can think of other setups and maybe simpler ones, quicker to run. Something we're working on at the Hadley Center is some sort of pattern scaling model, which is informed by an ocean atmosphere GCM run. So from that model, you get patterns of changes in temperature, in precipitation, on every parameter you need. And then monthly means. So you basically take monthly means of climate change. And then you use a weather generator here to drive a land surface model, which is pretty much the land surface model we've got in the climate model here. And we are gradually building this model using, including the carbon cycle and some impact modeling there. And because it's a land surface process model, you can estimate the emissions, the carbon emissions, the methane emissions, etc. On this, you can from there you can estimate radiative forcing, and that can feed back on climate change through that pattern scaling model. And the assumption here is that you can interpolate linearly climate change according to radiative forcing, which to some extent is right. So we've got a much faster model here. It's gridded, okay, but it's just 2D. It's just the land surface. And I think I understood from Steve that he's got a similar sort of approach where he's got the land surface model here, TEM for instance, and then the socioeconomic model here on the sort of interact with each other. So maybe that's a sort of framework where you can more easily couple the socioeconomics, the land surface, and the climate change without going into all the complexity of an Earth system model. So you can think of some more simple setups for some of the applications.
So the pattern scaling model is just EOFs or something like EOFs?
I'm not sure exactly how it's done. It's the Imogen model. It's documenting in the literature. I can provide some reference. Yeah.
Well, in SenGen, it's that Wetlands developed. There's patterns for greenhouse gas forcings, which are relatively the same for all the greenhouse gas forcings. Then you have a pattern for sulfate forcing, which is a different, actually direct and indirect are unfortunately different. So, and then you could potentially have something that had to do with land surface. In some sense, it's you could probably get to a level of complexity where you can reproduce pretty much the GCM to some extent. But it's a good way to explore the space.
Mm-hmm. Yeah, I'm not sure we've got the patent for sulfate aerosols, but certainly for the greenhouse gases.
These would be large scale circulation patterns, things like that. UFs of what patterns would come out of the GCM?
Well, for that particular
sort of large scale circulation patterns and things like that.
No, for that particular model, it's really surface temperature and precipitation on whatever is needed to drive the land surface model.
So what's the role of the weather generator in that?
Because you sort of save the monthly means, but monthly means is no good to drive vegetation. You need the variability, so you sort of disaggregate that monthly means into daily weather,
So
and that's what is.
The advantage of this is you can use a weather generator that generates realistic pattern of weather, which you don't necessarily get from the GCM. But on the second side, you don't. You worry about changes in extremes and so on, which are an issue throughout anyway. So that's an issue.
Yeah.
The weather generator is really using, at the scale of your analysis, current daily is applied to the monthly mean that you're getting from the pattern scaling model?
Well, you could have a weather generator which is calibrated against present-day observations, or you could calibrate it against UGCM. It depends what you want to do.
The problem is for future, you can't scale extremes or variability.
No.
So this, I mean, you can
That's
only,
not really
you
the
can only-
purpose of
you can only
that
scale
model.
certain things.
Yeah.
Right. So the question is, since we know that there's problems with the extreme, so you could potentially develop a weather generator that you come up with some paradigm for, okay, the GCM is showing a change in extremes, even if the current extremes aren't right, there's a change. So we let that change flow through into the weather generator formulation. I mean, you could say, well, if there is a change with this magnitude, then you downscale it to the impacts level. Here is what the impact would be. So you could do that sort of thing. And it's a very, so you've very clearly defined what you're testing, and it's not horribly complex, horribly computationally complex, and you get a well-defined answer. So you can do that.
So problems people have had in this regard is, for example, let's say the GCM shows an increase in precip for this month in this region. So now you have to ask the weather generator or inform it that there's going to be an increase in precip. And will that mean more days of rain, or more heavy rainfall days, or maybe even less frequent rain with even heavier rain? And at least in the agriculture models, it makes a tremendous difference which choice you make.
Right, but that's where we're sort of stuck at, just because we don't know the answers to those questions. So,
Right.
so David, if you can tell us.
I can tell you, would it be accurate?
The reason for this model was basically to investigate the carbon-climate feedback in a much quicker framework. And then, of course, depending on the question you want to answer, you've got to assess the assumptions which are going into that sort of model.
Yeah, the advantage of this is you can explore assumptions other than those that come out of the GCM, so you can explore a wider range, which is clearly useful.
So your patterns change according to the CO2 concentrations
Or relative forcing, yes.
So that means weather generator is totally independent of the pattern scaling model.
At the moment it is, yeah, I think so.
But it must accept the same mean, must generate the same mean value. Let's say you have patterns of precipitation. Presumably the weather generator can't be inconsistent with that in some way.
Oh, it's got to keep the mean.
It's got to keep the mean.
Yeah, oh yeah.
Then you can scale it by the feature.
We've mentioned the asynchronous coupling for the chemistry and the physical climate. So I think we've got to be inventive in simplifying these models and finding model setup which are easier to operate, because the full Earth system model, it's unlikely we can run many experiments with it. So there is some value in that. And then we've got MX, and we also have the concept of fast Earth system model. That's something the UK universities are working on. They're trying to get our climate model, but a much lower resolution with a good deal of parameterizations, and to use Earth system model for paleoclimate applications. Okay, so this is what we've been talking about this week, but I thought it was useful to illustrate it that way. And to some extent this had been discussed in Seville already, except that at that time we didn't really made a difference between emission and concentration. So basically I had this graph presented in Seville, but with emissions and concentration on the same plot. But on the top you can see the usual approach, bottom approach, where you start with your socioeconomics, you drive that you can estimate the emissions, and then you can estimate the concentrations on the surface temperature or the climate change. And the uncertainties will grow as you go through these different stages. And what we've been proposing this week is that we sort of prescribe the concentrations, and then we work backward the emissions, and then we work backward the implied socioeconomics, and in that direction we would estimate surface temperature or climate change. So this time it makes things a bit more complicated, especially in terms of uncertainties, but you can still use a forward approach to simulate the bottom-up propagation of uncertainties if you want. This is probably more difficult to explain to the policymakers, but I think we've demonstrated that there was a good deal of advantages as well.
Yeah, not just policy.
That's right. I think that's just the same thing with just emission and conservation. I'm going to skip that. Yeah, this is something I presented in Seville again when we came with this idea of the parallel timeline, which is pretty much what we've been discussing this week by opposition to the sequential timeline. So this was a sort of time scale. I think it's been changed slightly since then, but that was the time scale we were thinking about for interacting between the different working groups. Within a year from now, there should be this expert meeting on technical paper with benchmark emission trajectories, or it might be benchmark concentration trajectories instead. And then working group 1 can do the climate system modeling, and there can be a number of interactions between different working groups as it goes until AR5. At that time, we've seen a number of advantages. An early start for some of the physical climate runs, if you're in a position to do that. More consistency with SRES, because some of the benchmark scenarios here would be variants of SRES. Possibly a quicker delivery of AR5 as compared to the sequential timeline, where we really had some trouble to make it by mid 2013. It was almost impossible. And then some incentive for the different science communities to interact with each other. The disadvantages was well, we've got to make sure that the choice of the emission trajectories here, or the concentration trajectories, come with a formal assessment process, and that was one of the concerns of Susan, for instance. It's still not clear to me how the short-lived species and the land use changes will be made consistent with the CO2 trajectory in the benchmark scenarios. We can assume something, but then if it proves to be inconsistent, then we've got somewhat of a problem. I mean, we've got to make sure we explore enough of the dimension in short-lived species and land use so that we can use the EMIC to remove the inconsistencies if there is any. As I mentioned before, the propagation of uncertainties is more complicated to do and to explain, but I think we can work it out. Yeah, I'm not sure why I wrote this one. Potential lack of consistency between global and regional climate trends. Yeah, not sure. Not sure about that.
Yes, I mean now if we go through this proposed, this kind of backward kind of thing, it's still working the same way, right?
Yeah, pretty much. Yeah, I think.
Actually, it's not. It really, if you're working with this backwards type of thing, it really constrains what you need. If you have a stabilization path, well, it's a stabilization path, and that's doesn't require as much input. So it's much simpler. I think it's another pro. You don't need as much.
Yeah.
You need the other gases. But.
And I think the question is how many iterations you can do before we have 5. I mean, if we start somewhere here with the benchmark scenarios and we find some inconsistencies, maybe there will be a pressure to rerun again, and not sure we'll have time to do it before we have 5.
I don't think if everyone does the same benchmark, there is no such thing as consistency anymore, because they all give a different answer, and some of them may be harder to realize than others, but the benefit is you have this comparison. So I don't actually see a good way to do it any other way. I mean, with this first generation of models, if you have this prescribed, particularly CO2 trajectory, concentration trajectory, maybe the Hadley Center dies back the Amazon, and that just is extremely expensive or unrealistic. But that's okay. That's a result. It's still a legitimate result, and you still have a comparison between the models. But the models are going to not be consistent. They're all going to give a different result in terms of the carbon fluxes. So,
basically agree. I think we all agree. Well, this is a slide Peter Cox has already shown, what I just want to point out is that we start to have this non-radiative forcing there as drivers to the system, and for instance irrigation, damming, so anthropogenic changes to the water cycle, land use changes, so that comes on top of the emissions which we've been having so far. I could have had urbanization here that is changing the land use and the surface fluxes quite a bit as well. I'm now going to show a bit of research which has been done in the Hadley Center on this climate chemistry, carbon cycle interactions over the last few years. So this is a result from Colin Johnson using the STOCHEM model, which was driven asynchronously with the HCM3. And what he showed is that accounting for the climate feedback on the methane cycle, you would end up with a smaller concentration than not accounting for the climate feedback. And that's basically because there is an increased concentration of water vapor, and that leads to a greater destruction of methane. And you've got something here which is about 500 ppb, so it's not negligible. Is that consistent with what you get, Jean-François?
I don't think we've done A2 scenarios.
Yeah, that's an A2.
20 to 2100. But
the sign of the feedback.
Absolutely. Yes, there's that.
And something fairly similar for ozone. Again, if you account for the climate feedback, that reduce your ozone significantly again because of the destruction which involves the water vapor molecule. However, so that's a negative feedback. However, there is a positive feedback in the sense that natural emissions of ozone precursors will probably increase with a warmer climate.
Particularly VOC, is that so?
Yes, and this is the curve here, which shows the temperature, and that's for, you see, 25th of July to 12th of August, so that's a rather short period, and there's been a period of high temperature here in the UK, and then the pink curve here shows the emission of isoprene, and that really responds to temperature. What's not clear to me, and I don't have enough background in ecosystem modeling to know whether that's true or not, whether that sort of correlation would hold on longer time scale. If you've got a warmer season, will you get a larger isoprene flux for that season as compared to a cooler season? I think it does for some of the plants, but maybe not for some others.
Does isoprene go into, what does isoprene then turn into? I mean,
and there's some conditions that will increase your ozone production.
Ozone.
We haven't done that run yet. Another feedback we've looked at is the feedback involving wetland emissions of methane. So we had some modeling of wetland, which is well, basically we look at the water table, and we've got a subgrid distribution of the water table on where it comes to the surface, and we say it's a wetland. And the fraction of wetland which is simulated offline, so if we drive the model offline with observed climate, observed precip and temperature and so on, is not too bad as compared to observations. So this is observations, this is what we get offline. If we put that scheme online in the model, because the physical climate isn't perfect, then you get something which is not as good, but still reasonable as in comparison to observation. So the model is doing not too bad a job to.
So do you keep track of the depth of the water table?
Yes. And wherever we've got.
So from like just a fraction to whatever, no matter how much. So you have a water budget that raises the water depth.
Yes, you've got the water table, and then you've got the subgrid scale distribution of the orography, and wherever the water table is higher than the surface, that's your wetland.
Africa seems to be most problematic.
Sorry?
Africa, what is the cause for the difference?
Yeah, that's right. Yeah, not sure why.
Too much precipitation out of the Congo. Doesn't mean it always is.
Yeah.
Oh,
There is an issue there. Okay, then we can model emission of methane as a function of temperature, and I think that's some work done by Nick Gendley with Peter Cox as well. And she's done a number of model, and in general she's well, there is this Q10 parameter by how much your methane emission are going to change with a 10K increase in temperature, and she's sort of tuned that against observation. So she's minimized the departure to observation for current climate, and she's got a range of parameters here, but it doesn't make much difference. In all cases, she roughly predicts a 200 teragram of methane change in emission from now until 2100, and I think that's an A2 scenario again. So the emissions would go from 300 teragram of methane to about 500 teragram. But that's not much in terms of temperature change. We're just talking about 0.15 K by 2100 in an A2 scenario. So you can argue that's a fairly small climate feedback. Yes? We've talked as well about ozone effect on plants, and this is just pictures which show what ozone can do to plants here. They don't like it. It's quite well documented in the literature. Of course, you've got a different response by different plants. So these are basically crops, different types of crops: soybeans, corn, wheat. I think no, sorghum, corn, wheat, soybean, peanut, and cotton. Yeah.
So crops are in some sense, maybe more sensitive in a lot of things because we manage them. So what are natural
There've
vegetation?
been some phase experiments with CO2 fertilization, but also some phase experiments with ozone enhancement. There is
the Duke phase experiment has done some ozone in their hardwood systems. And the group up in New Hampshire, Scott Ollinger's, the peanut model, specifically does ozone, and that models the process of almost ozone, high ozone and plant response.
Because I noticed, for example, sorghum, which is probably the closest to a natural plant up there, has the least response. It has a very, very, small response unless you get up to 100.
So that's the mean seasonal ozone concentration would be 120 ppb for the whole season. Is that what this shows?
Maybe you know more than I.
I don't know that much. Well, I think what that is, it's a mean seasonal concentration. So as the seasonal concentration increases, the various response levels change. But if you look at, sorghum, which has a very
the growing season,
malcophilous or a rather leathery type of a leaf, versus cotton, which is much more soft, then there is a sort of a relationship there between how the consistency of the leaf and where how well protected the stomata are.
But we've sort of might have bred out some of those resiliencies from our crops. So.
Right. But a lot of the hardwoods like aspen and maple are pretty susceptible, broadleafs, and similarly the pines can be as well.
Now you can.
What are just since I don't really know the numbers, what's sort of background ozone, away from like Kansas or something?
Jean-François, we're pretty much in that range already, right? 20 to 40 ppb.
40, yeah.
So we're pretty much in the range where you start to have some decrease in primary productivity. Well, you can probably argue that you can adapt the crops so they can resist better, so you can trick you. So, but the natural ecosystems still have a response. What's important to note is that CO2 has a mitigation effect. You see that the start point here, where the ozone isn't good for the plant, is higher under 2 times CO2 than under 1 time CO2, and that's because of the stomatal closure and higher concentration of CO2, so the ozone effect is less.
Is this a modeled result, or is this an observational result? That you double CO2 and increase ozone, you don't have as
I
much?
think that's more like a model, but in the phase experiments they've done, the experiment where they increase the CO2, or they increase the ozone, or they increase both. I'm not sure if they observe that mitigation effect or not.
Yeah, I don't know, but that's definitely a model result. Okay. Based on how we understand how the stomata responds to double CO2 versus ND.
Okay. So yeah, Steve Sitch has come with some parameterization of that, and he's improved it. So I'm not going to show his latest result. It's some old result. It has probably changed since then. This is some sort of ozone changes that is predicted under A2 scenario by 2100. So again, it's pretty much the extreme of what you can get, but increase of 10, 20 ppb over some regions, or even larger there. Whether that's realistic or not, I'm not sure. Steve Sitch makes the point that where you get the largest ozone changes is also where you get the crops, so that can be a problem. And what he's done is he's worked a parameterization of that ozone effect on plants, which looks something like that, and is based on the well, it's calibrated against observation, but it's based on the ozone concentration. And what he gets is a significant reduction in the carbon which is stored in vegetation and soil. So this is the total carbon stored in pre-industrial, and this is in the change by 2100, which is just due to that ozone effect under an A2 scenario.
But this is like A2. That's a really high-end, unrealistic ozone change for most cases.
Yeah, probably it's really the
almost certainly
upper.
Actually.
That's probably the upper bound of what you can get.
Yeah.
But he's talking about a sink which is 130 petagram of carbon less.
And then in the mitigation scenario, you absolutely always have less ozone because you're shifting from fossil fuels. So
absolutely.
You know, in a practical mitigation scenario, this would be nowhere near this effect.
Mm-hmm.
Is the nitrogen deposition taken into account?
No. So that's an earlier version of his results. I'm not sure about the new results, but I think they were roughly in the same order of magnitude. So 130 pentagram of carbon, which if you divide by 2 will give you 65 ppm in the atmosphere, and then you could argue that half of that will go in the ocean anyway, so you're talking about a feedback of 30 ppm under that particular scenario. So something, yeah, which is something you want to consider, on the edge of what you want to consider. We've looked at how sulfate aerosol could change in a warmer climate. So this is the sulfate distribution here for present day, and just by changing the climate, we're not changing the emissions, the anthropogenic emissions, but just changing the DMS. The DMS responds to climate, and the emission of DMS would respond to changing wind speed and temperature and everything. You get slightly different distribution of your sulfate. You can't see much difference.
A model of DMS emissions.
It's done. Yeah, but the coupling is all done offline sequentially. Okay. So we've got an experiment of climate change, which has then driven an ocean carbon model, and then we're using the DMS of that model back in the atmospheric model. It's all decoupled. Okay. And you don't see much of a difference here, but I'll come to the difference later on. So that is just changing the emissions of DMS. And then if in addition you change the precipitation, you're going to change the scavenging of the natural aerosol and the anthropogenic aerosol. And again, it's for fixed anthropogenic emissions. You get that sort of distribution. And if now you look at the difference between these two, you're not talking about large changes, but what is interesting is that you've got, on average, less sulfate in the northern hemisphere because there is more precipitation, so the lifetime of your sulfate aerosol decrease. Whereas in the southern hemisphere, you get a bit more sulfate because the DMS increase is larger than the decrease by the precipitation. So you get a bit of a bipole and extra warming here and extra cooling there. It's not much. You're not talking about large numbers. I think here it's somewhere 10 pptV of sulfate. Similar thing if you look at sea salt. At least in our model, climate change is increasing the wind speed over some part of the ocean, so you increase your sea salt production, and your burden of sea salt is larger in 2 times CO2 conditions than in 1 times CO2 emissions. If you now account for changes in precipitation as well, this is what you get. And if you look at the difference between these two, you again get a bit less sea salt in the northern hemisphere and a bit more sea salt in the southern hemisphere. So again, something which will tend to warm the northern hemisphere and cool southern hemisphere. But we're not talking about large numbers here. Probably 5-10% of the
microgram or 2 micrograms.
This is in microgram per cubic meter, and yeah, this is 0.5, 1, 2. It peaks at 4 maybe here. And that's a bit model dependent because not every model will predict the same change in wind speed at the surface.
Yeah, I think CCSM doesn't see much difference.
Yeah, this is the LMD model, the French model, and I think Hadley Center doesn't see much of a change in wind speed. So this is back with the Hadley Center model, and this is some work done by Stephanie Woodward, and she looked at dust emissions present day on 2100, and this is a simulation where the Amazon died. Okay, so the bare soil fraction here increases dramatically, and this is the dust loading present day on 2100, and I think there is about a factor of 4 difference because of changes in bare soil and changes in climate. The interesting thing is that these two don't sum up because where you deforest, where you bring all this bare soil, you also increase the wind speed dramatically because the roughness length decreases. So the two effects don't sum up. It's far from linear. So a large increase in dust load, but again, it's particular to this extreme scenario here.
Is there also changes in area of land that's cultivated and things, or is this only a precipitation response?
Yeah, here this is only natural vegetation. So you could argue that Brazilian would plant some crops here, so it wouldn't be bare soil. They would irrigate or they would do something. So yeah, it may not be the actual.
Paleoclimate people say that you had more dust load in the ice age. So in the present world, we have least load of dust. And I think it's counterintuitive. Have you performed some paleoclimate?
We haven't done some paleoclimate experiments. Some last glacial maximum experiment with that model. I know some people did. No.
Paleoclimate experiments have a lot of difficulty getting the estimated increase in dust.
Okay, in terms of radiative forcing, that doesn't make a lot of difference in terms of global radiative forcing because there are regions of plus and regions of minus, so it's just increasing the gradients in places, but it's not making a huge difference in radiative forcing.
In spite of the fact that you've increased the amount of dust by, did you say the burden changed by a factor
by a factor
of 4?
of 4, yeah. But you've got the long wave and the short wave effect, and they sort of cancel each other. So you see there are more contrast, but the global mean radiative forcing hasn't changed that much.
If you don't look at the, well, okay, sorry, I should. If you don't look at the net forcing, but the short and the long wave side, is there a big forcing?
Yeah, they would probably, yeah. I would expect them to scale linearly to the burden, more or less. Yeah. Okay. Yeah, just to update us with our plans, to put this into context, we had the HADCM3 model, which has been used for the first assessment report. It's been used for AR4 also. There have been runs from HADCM3 which has been submitted to AR4. And that's also the model we're using for ensembles because it's cheap now on today's supercomputers. So we use it for the QAMP ensembles, which are perturbed physics experiments. We use it for the very experimental work we do on decadal variability as well. HADGEM1 then has been the new model, which had some of the physics of HADCM3, but it had a new dynamical core. And HADGEM1 has been used for AR4. HADGEM1 stands for Hadley Global Environmental Model, but it's not an environmental model. It doesn't have much of an Earth system in it. It's just had a number of aerosol species, and that's it. And what we are now building is HADGEM2 Earth system. So it's mostly based on HADGEM1. We've improved the physics a little bit, so there is a physical package on top of HADGEM1, but we're not talking about major differences. It's improving the variability in the tropics a little bit, but still ENSO isn't good enough. We've improved the aerosol quite a bit as compared to HADGEM1. And then we are coupling the terrestrial on the oceanic carbon cycle, so that is the MOSIS 2 land surface process. We're using a new soil carbon model, which is ROT-C, Roth-Hansted carbon model. So that's a difference with the with Peter's experiment, which was based on HADCM3 low resolution carbon, where he had a different soil model with just one pool. Now it's going to be 4 pools of carbon in the soil. We're still not sure whether there will be a nitrogen limitation for the land carbon cycle, but if there is, it's going to be something very simple. We're using the Trifid dynamic vegetation model, which is what Peter used in his 2000 experiments. So that's not going to change. The ocean carbon model will be improved. They used to have HADOC, which is the classical NPDZ model. And now I think there will be 2 classes of phytoplankton, so there's diatom and non-diatoms. So that's a difference with the 2000 experiments. There's a bit more complexity. And then on the atmospheric chemistry, it's still unsure, but we'd like to have some sort of chemistry there. So this is HADGEM2ES. This is the main strand of development in the Hadley Center in terms of Earth system modeling.
What kind of resolution are you talking about?
With same resolution as HADGEM1, which is N96, so that's 192 points in longitude, about 1.8, 1 degrees. In parallel to that, we're working on HADGEM3, which is pretty much the same atmosphere model as HADGEM1, so HADGAM. A stands for atmosphere here. So it's HADGAM1 plus this physical package, but a new ocean model, which is a NEMO ocean model, and that's becoming, it's a community ocean model in Europe. It's based on the OPA French model, but it's being adopted now by many people, ICMWF, Hadley, Toulouse people, and there's quite a community around that ocean model now. So this is sort of next generation of the physical ocean atmosphere model, and that goes in parallel. But the plans for AR5 is really around HADGEM2ES, and if that comes in time, then there might be some HADGEM3 runs, but that's not for sure. And in any case, we're not working on a time scale to fit AR5. AR5 is not the driver for that model, let's say. At the same time, Colin Prentice and the Quest community is working on a prototype Earth system model, which will be the next generation Earth system model as compared to this one. So again, that's post AR5. That's not for AR5. And there is more involvement of the universities in that model. And the idea is to use hydrogen-free, so they would need some hydrogen-free prototype to start with, but a low resolution to start with, because they're pretty much interested in paleoclimate as well, so they want something quick. It would have the full UKCA chemistry, the Joules land surface model. On Joules is basically Moses 2. Joules is based on Moses 2, but it's being made a community model now, and we're going to develop it with the universities, and it's going to include ROT-C and the new dynamic vegetation model in it, something someone called Rosie is working on, maybe you know her. And also the ocean carbon cycle will be new generation with that concept of dynamic green ocean model, where there would be functional types for the planktons, so very similar to what is done over land. And this is something going on at the same time, but on a longer time scale.
What is UKCA?
UKCA is UK Community Chemistry and Aerosol Model. So we sort of, the Hadley Center now is working more and more with the UK universities, and we've got this community model for chemistry and this community model for the land surface processes on carbon cycle and dynamic vegetation. It's less clear for the ocean carbon cycle. We've got to be more joined up than we are at the moment.
So are you going to use the same parameter values in the triffid that produced the Amazon die-off? I mean, when you look at that comparison of all the the amount of extra carbon that stays in the atmosphere, that model is much more sensitive than all the others.
I'm not sure whether it's because of triffid, whether it's because of the soil carbon.
Peter Cox, and he said the die-off of the Amazon was only 10% of this difference. Or the feedback.
The feedback is mostly from soil carbon. On the Amazon, it's very...
That was a consequence of the model, but that model is a lot more sensitive in terms of the global amount of extra carbon that stays in the atmosphere than all the others.
Oh yeah,
so you're still going to have that as an outlier?
No, well, we don't know until we do the experiments. But Peter used HCM3 with triffid, with haddock, and with that one pool soil carbon model. There will be a number of components which will be same, but there will be also a number of improvements as compared to Peter's model. In particular, triffid will be same, there won't be any change, but the soil carbon model will be different now. And the ocean carbon model has been improved as well, or the complexity of it has been enhanced. So I don't know what we'll get. And these are just general conclusions. I think it's very basic. ESM offer new and great perspectives to investigate climate change in a more holistic manner, including these non-radiative forcings and the feedbacks. But there's a number of challenges as well, as we've seen. Supercomputing is an issue for these models, so we've got to think about decoupled approaches when they are appropriate. Thank you.